Today's topic is Coulombs Law. Under this topic, you will learn how do we calculate electric force using Coulombs Law. Then we will compare electric force with gravitational force and see an example as well. Each point charge Q1 or Q2 exerts a force on the other. Regardless of whether the forces are attractive or repulsive, they are directed along the line between the charges and have equal magnitudes. The electrostatic force that stationary charged objects exert on each other depends on the amount of charge on the objects and the distance between them. Experiments reveal that the greater the charge and the closer together they are, the greater is the force. The French physicist Charles Coulomb carried out a number of experiments to determine how the electric force that one point charge applies to another depends on the amount of each charge and the separation between them. His results, now known as Coulombs Law, is stated in the next slide. The magnitude F of the electrostatic force exerted by the point charge Q1 on another point charge Q2 is directly proportional to the magnitudes of the charges Q1 and Q2 and inversely proportional to the square of the distance between them. K is the proportionality constant. Its value is 8.99 into 10 raised to the power 9 Newton meter square per Coulomb square in SI unit. This equation gives the magnitude of the electrostatic force that each point charge exerts on the other. It does not give the direction. The electrostatic force is directed along the line joining the charges, and it is attractive if the charges have unlike signs and repulsive if the charges have like signs. Now, before I compare Coulomb's law with Newton's law of universal gravitation, it's worth mentioning to understand two more things in Coulomb's law. First, the magnitude of a variable is sometimes called the absolute value and is symbolized by a vertical bar as indicated here, to the left or to the right of the variable. Okay, as you can see here for Q1 and Q2, there are two vertical bars. Thus, this denotes the magnitude or absolute value of the variable Q, which is the value of Q without its algebraic plus or minus sign. As an example, if charge is minus 2 Coulomb, then if we put a vertical bar around this symbol, that would indicate the magnitude of this charge, that is only 2 Coulomb. Okay. Secondly, it's a common practice to express K in terms of another unit which is constant epsilon naught, by writing K is 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space and its value is 8.85 into 10 raised to the power minus 12 coulombs per Newton into meter square. Now, as you can see here, I have listed few similarities and differences between Coulomb's law and Newton's law of universal gravitation. It must be noted that Coulomb's law has a form that is remarkably similar to Newton's law of universal gravitation. The force in both laws depends on the inverse square of the distance, as you can see from these equations, and is directed along the line between them. In addition, the force is proportional to the product of an intrinsic property of each of the objects, the magnitude of the charges in Coulomb's law and the masses in the gravitation law. However, there is a major difference between the two laws. The electrostatic force can be either repulsive or attractive, depending on whether or not the charges have the same sign. In contrast, the gravitational force is always an attractive force. Moreover, electric forces are far stronger than gravitational forces. So, Coulombs apparatus. Coulomb developed his law using a torsion balance. It is an apparatus which is used to measure small forces. So he measured the force between the 2 point charges or two charged spheres by the amount of twisting in the wire. Superposition principle. Up to now, you have been learning the electrostatic force on a point charge Q1 due to another point charge Q2. Suppose there is a third point charge Q3 also present here. So what would be the net force on Q3 due to both Q1 and Q2? It's very convenient to deal with such a problem if we do in parts. Okay, I have listed the steps here. So we will find out or determine the force exerted on Q3 by Q1 and Q2 in parts. First we will ignore Q2 and we will find out force exerted on Q3 due to this point charge Q1. In the second step, we will find the force on Q3 due to Q2. That time we will ignore Q1. So the net force on Q3 will be the vector sum of these two forces. I have explained in a simple diagram here.